Yeah. All right, so welcome everybody back to the point distribution webinar. Today we have Iosevich from the University of Rochester talking about point configurations and frame theory. Alex?
Okay, thank you very much. It's an honor and a pleasure to be here. So many old friends, so many new faces. This is wonderful. So I didn't know precisely what the audience was going to be. So I designed a very basic and user-friendly talk where my main goal is not to bombard you with the latest results, though I'm going to mention a couple, but rather I chose a fairly narrow task, and that is to expose a connection between some certain problems in frame theory and certain problems involving point configurations. So my biggest passion in mathematics is, as some of you know, is connecting different areas. And this is what I'm going to talk about. So also let me mention from the start, please interrupt me anytime for any reason. It is not going to be a great tragedy if I cover a little less than I planned. Okay? All right, so let's get started. So on point configurations and frame theory. Oh, let's see. There we go. So one of the oldest and most far-reaching problems of modern mathematics is the question of expanding functions into linear combinations of sines and cosines. I understand that this is not news for any of you. Nevertheless, I thought we should frame the discussion. And also, I'm a big fan of quotations by people from various areas of learning. And I've recently discovered this quote about Fourier analysis by Bruce Hood, who is a clinical psychologist. So in my deep, dark past, before I studied mathematics, I studied things like psychology and history before I saw, before I adopted the true faith. And so I found this wonderful quote. So Fourier's theorem has all the simplicity and yet more power than any other familiar explanations in science. Stated simply, any complex pattern, whether in time or space, can be described as a series of overlapping sine waves of multiple frequencies and various amplitudes. So I find two things about this quote absolutely wonderful. One is that it's great that people from other area of learning are talking about us. But second, and this is certainly not Bruce Hood's fault, but roughly 99% of the beauty of Fourier analysis is buried precisely in the intricacies that he does not mention, right? In other words, it's not that any complex pattern can be described as a series of overlapping sine waves of multiple frequencies. As it happens, if we make our terms precise, some phenomenon cannot be modeled in this way. And this is part of what I'm going to discuss today, okay? All right, so the main theme is that I will attempt to describe, at least this is the plan, in simple and direct ways, how the study of orthogonal exponential bases or Fourier bases and related problems are related to the study of point configurations, okay? So understand that there's a lot buried behind those terms, point configurations, and it means different things to different people. Nevertheless, some commonalities exist. So what is the basic frame theory question under discussion here? So given a bounded domain omega in Rd, does L2 of omega possess an orthogonal or approximately orthogonal, all these terms will be made precise, basis of exponentials? In other words, basis of the form e to the 2 pi I x dot lambda, where lambda lives in some discrete set, capital lambda. And we shall refer to this set as a spectrum, as is the usual convention. Spectrum, of course, is one of the most overused words in mathematics, but what can we do? Okay. All right, so, and then what do we mean by point configurations for the purposes of this talk? So the rough question is as follows. Given a discrete set of points with a suitable density condition, and I'm being, for the time being, quite vague about what I mean by density because it's going to depend on the context. Roughly speaking, it's the number of points in a large ball of a given radius, okay? Does this set contain a congruent or a similar copy of a given point configuration? For example, is every possible distance realized? Can you recover every similarity class of any triangle, etc., etc., etc.? So once again, the theme is to connect the study, to provide some connections between the study of orthogonal exponential basis and the study of point configurations, by which I really mean Erdos type problems involving recovering configurations of points inside sufficiently dense sets. Are there any questions before I proceed? No. Okay. So my desire to ask questions of the audience is partly motivated by the fact that I'm teaching calculus for biological sciences this semester. Okay. All right. So just a very quick aside. This talk is not really about the theory of orthogonal exponential basis. It's about what I said. But just as a quick aside, let me give you a little bit of a context. So for a long time, the study of orthogonal exponential basis revolved around the Fugletti conjecture. And normally when conjectures are mentioned, one mentions when the conjectures were formulated. In other words, the birth date of a conjecture. But here we have a birth date, and there's also the date of death. So this conjecture died a very miserable death at the hands of Terry Tao in 2003. In fact, there's this beautiful memory that I will, something I'll never forget, is that I received a phone call in 2003 when the Terry Tao's paper was posted from Michael Lacey. And he told me that the Fugletti conjecture was disproved. And I'm ashamed to say that I hung up on him. I was like, Michael, I don't have time for this. And then I realized that he was right, and I called back and apologized. Okay. And so the Fugletti conjecture says that if omega in Rd is a bounded domain, then L2 of omega has an orthogonal basis of exponentials if and only if omega tiles Rd by translation. Okay, so why is this a reasonable conjecture? Well, we know that the cube has an orthogonal basis of exponentials. This is a classical Fourier series that we all know and love. And of course, cube, you can tile Rd by translating a cube by the usual lattice, integer lattice, right? So this is certainly consistent with our sort of basic mathematical instincts. And also, it's not difficult to show, this is a quick exercise in Poisson summation formula, that if a domain tiles by a lattice, then the dual lattice gives you an orthogonal exponential basis. And conversely, if a lattice gives you an orthogonal exponential basis, then the dual lattice tiles your domain. Okay, and this is a photo of Fugletti. Now his name is not really pronounced Fugletti, so people from Scandinavia tell me that it's pronounced something like Foulier, but when they say Foulier, nobody knows what I'm talking about, so I say Fugletti. Okay, it's just like pronouncing Russian names correctly. Everybody looks at you funny because they don't know what you're saying. Okay, okay. So as I said, Fugletti proved that this conjecture holds if either the tiling set or the spectrum is a lattice. Okay, so even though Terry Tao disproved the conjecture in 2003, and how he disproved it and some of the consequences of this could be a subject for any number of lectures. This is not the point of this talk, but nevertheless, the conjecture still holds in many cases. For example, the conjecture was proven to be true for two-dimensional convex sets, and this is a result due to Netzketz, Terry Tao, and myself. And very recently, in an absolutely beautiful paper, the convex version of Fugletti's conjecture was established for in all dimensions by Nir Lev and Mate Matolci. Okay, and so Fugletti conjecture continues to inspire a lot of interesting work, I believe, in combining combinatorial arithmetic and analytic techniques. Okay, so this is the background. So now let me go ahead and get back to the theme of the talk, which is establishing concrete, simple connections between orthogonal bases and point configuration problems. Okay. So as I said, in the case of the unit cube, everything has been well understood for a long time, though even there, interesting questions can be found. For example, it is true that integer lattice gives you an orthogonal exponential basis for the unit cube. It is also true that the integer lattice tiles the unit cube. However, one can ask, and I think it's very interesting to ask, and there have been many papers written on this, is what are all of the tiling sets and what are all the spectral sets for the unit cube, okay? And so one of the results in this direction that let me just mention in passing is a theorem that was proven at exactly the same time by, so the Lagarius, Reed, and Wang, and simultaneously by Steen Peterson and myself in 2001. And this theorem is an example of a result that I like to sort of jokingly tell my non-mathematician friends is why people hate mathematics. The question was, what are all the sets that tile the unit cube? And what are all the sets that give you spectra for the unit cube? We managed not to answer either of those questions, but we did prove that those sets are the same. In other words, a discrete set is a tiling set for the unit cube, if and only if it's a spectral set for the unit cube. So in the style of pure mathematics, we managed not to shed any light on what those sets are, but we showed that they're the same. Okay. Okay. But now let's move on to a different type of a domain. Suppose, consider the unit ball in dimensions 2 and greater. Does L2 of the ball possess an orthogonal basis of exponentials? In other words, this was a question raised by Ben Fugletti in 1974. In other words, can we have a Fourier, orthogonal Fourier basis on the unit ball in the same way that we have them on the unit cube? And so let's examine this question, and this will be our first foray in this talk into this connections, into this family of connections that I plan to describe. So let's imagine for a moment that there is an orthonormal basis for L2 of the ball, and it's generated by a spectrum capital lambda. So then lambda is a separated set, so the points don't get closer together than a certain amount. This is very easy to prove. And the density of the set is just the volume of the ball. So in other words, if you intersect lambda with a large ball of radius r, you divide by the volume of the ball, you take a limit, the limit exists and is equal to the volume of the ball. Okay, this is the classical Berling density theorem. Okay, and what does orthogonality mean? Orthogonality means that for every lambda not equal to lambda prime, the Fourier transform of the ball at lambda minus lambda prime, which by definition is just this integral, is equal to 0. This is just the orthogonality condition, okay? So where are the point configurations? They're coming, I promise you, okay? So we have a very exact formula for the Fourier transform of the indicator function of the ball, okay? And I tried to even get the constants right in this formula, even though this is not easy for me. So the Fourier transform of the ball at lambda minus lambda prime is 2 pi times the distance from lambda to lambda prime minus d over 2 times the Bessel function of order d over 2, evaluated at 2 pi times norm lambda minus lambda prime, okay? And the zeros of Bessel functions are uniformly separated. This is a simple integration by parts argument. Moreover, this has been known for a couple of centuries. And what this tells us is that if you take the spectrum and you intersect it with a large cube of, let's say, side length r, then the number of distinct distances, because notice that that this condition here is about the zeros of the Bessel function, right? The only way this is 0 is if the distance from lambda to lambda prime is 0. Is that the distance from lambda to lambda prime is a 0 of the Bessel function of order d over 2. And since these zeros are uniformly separated, the number of distinct distances between the elements of the spectrum intersected with a cube of side length r cannot exceed a constant times r. Okay? On the other hand, the density of lambda implies that the number of points of this putative spectrum inside the cube of side length r is approximately r to the d, because we have non-zero finite positive density, right? So all of a sudden, we took a perfectly respectable looking functional analysis problem and we converted it into a problem about point configurations. Okay? In other words, what we are forced to conclude is that if the ball, L2 of the ball, does indeed have an orthogonal basis of exponentials, then this leads to the existence of this magical set, which has on the order of r to the d elements, and think of r as being rather large, but the number of distinct distances among the elements of this set is less than or equal to a constant times r. And those of you who are familiar with Erdős style combinatorics, this is now highly reminiscent of a very famous problem, and this is where we now turn our attention. Okay? So Erdős conjectured in 1945 that the set of size r to the d, I'm stating it in a form that's convenient for us, in dimensions bigger than or equal to 2, determines at least r squared distinct distances. Now, the notation here is that this is the Cherry-Tile notation. 1 squiggle means that we are subsuming constants, and 2 squiggle means that we are ignoring arbitrarily small powers of r to the epsilon. Okay? So this allows us not to worry about vectors, about logarithmic vectors. So imagine that Erdős conjecture were true for a moment. We will discuss what is known in a bit. So then the set of r to the d would determine at least r squared up to logarithms distinct distances. But this magical set that we have constructed based on the assumption that L2 of the ball has an orthogonal basis of exponential implies that there are r to the d points that determine fewer than a constant times r distances. And this is, of course, inconsistent with the Erdős distance conjecture and would lead to an instant contradiction if we knew enough about the theory of the Erdős distance problem. So what is known? So this is Paul Erdős. I mean, I became really happy a number of years ago when I discovered that I can just lift pictures of the internet and put them in my talk. I mean, this is really quite fun. So the conjecture in its full glory is only known in R2. And this is a beautiful result, very deep and beautiful result due to Larry Guth and Nets Katz. It was proven in 2011 and published in the Annals of Mathematics in 2015. But we do not need the full glory of the Erdős distance conjecture. We only need to know that r to the d points in d dimensions determine more than a constant times r to the alpha distances for some alpha bigger than 1. And this result was established by Leo Moser in 1953 in his PhD dissertation. Okay? The point that I want to make here is that, and to me, this is a very interesting perspective, is that while the Erdős distance problem is a very deep and complicated problem, what we actually need to know in order to disprove the existence of the orthogonal exponential basis for the ball is very little. In other words, to prove that the number of distances is more than constant times r to the alpha for some alpha bigger than 1 is fairly elementary combinatorics. And this is an illustration of a phenomenon that I particularly enjoy in mathematics. When an open problem in one area is solved using fairly elementary techniques from another area. In other words, where the biggest trick is not, where the biggest trick is to recognize which area of mathematics a given problem belongs in. Okay. Okay, so this is, all right, so let's now establish a contradiction very carefully just to make sure. So once again, we intersected our putative spectrum with a cube of side length R. We have shown by using elementary properties of orthogonal bases that that set has size approximately R to the D, but because of the zeros of Bessel functions, it determines fewer than constant times R distinct distances. And this is impossible by the aforementioned results on the Erdős distance problem, okay? And this follows that L2 of the bowl does not possess an orthogonal basis of exponential, and this is a result due to Netscat, Steen Peterson, and myself from roughly 1999. Are there any questions before I proceed? Okay. All right. So another principle involving point configuration that enters the world of exponential basis is the Erdős integer distance principle. And this is the one, I mean, this one is, I think, particularly beautiful, and it quite often arises in various Olympiad style problems. So what it says is the following. So if A in Rd is an infinite set such that the set of distances is a subset of the integers, then A is a subset of a line, okay? So this result was, so this theorem was published by Erdős and Rogers in 1946, I believe. And it was quite interesting. If you look at the publication, it's a very nice paper where they give a nice 4 or 5 page proof of this. And then 6 months later, there's a follow-up by Erdős where he says, oops, I am sorry. This can be proved in 2 lines. And he gives a really beautiful proof using hyperbolas. Okay, so I'm not going to go over the proof today, but it's really, really pretty. And I so very much recommend you take a look at it if you like these sorts of things. Okay, in higher dimensions, the argument is not much harder. It's just a matter of setting up the geometry. Okay, and so here's how this result enters the study of orthogonality, of orthogonal exponential basis and related problems. So this is joint work with Misha Rudnev from 2003. So let K be a bounded convex symmetric body with a smooth boundary and everywhere non-vanishing Gaussian curvature. And let e to the 2 pi I x dot a denote a set of orthogonal exponentials in L2 of K. Okay, so I'm not specifying here if capital A is finite or infinite. It's just some set of orthogonal exponentials. Okay, then if D is not congruent to 1 mod 4, then capital A is finite. Okay, in other words, when the dimension is not congruent to 1 mod 4, then A actually has to be a finite set. If D is congruent to 1 mod 4, A may be infinite. In other words, they're actually examples of bounded convex symmetric bodies where A is infinite. And if A is infinite, then it must be a subset of a line. Okay, so I don't have time to discuss all the intricacies of this theorem, which keeps popping up in a variety of disguises to this day. But let me just briefly describe how this particular point configuration principle, namely the Erdős integer distance principle, arises in this context. So, so there's an old formula that's for the Fourier transform of a symmetric convex set with a smooth boundary and non-vanishing curvature. In the West, we believe that this formula due to Hertz. In the East, many people have pointed out to me that it was published in a book by Gelfand and Shulov 10 years earlier. I don't get into this dispute anyway. So this formula is known, and it says that the Fourier transform is equal to the, so this factor, and then sine of 2 pi of rho star minus d minus 1 over 8 times the decay, norm c to the minus d plus 1 over 2, plus a remainder, a small remainder. And here k is the Gaussian curvature and the boundary, and rho is the Minkowski functional of the convex body k, and rho star is the dual functional. Okay. And from this formula, it is very easy to deduce that if two exponentials are orthogonal, then this dual distance, rho star, is up to a small error, a shifted integer. Okay? Now, the Erdős integer distance principle that I described before doesn't exactly apply. It was proven only for Euclidean distances, and it was not proven in the case where there are errors involved. But it turns out that one can modify the argument of the Erdős integer distance principle, and it still works in this approximate setting and proves the result that I stated. Okay? So once again, the result that this leads to, just going back, is that if you have a bounded convex symmetric body with a smooth boundary and everywhere non-vanishing Gauss curvature, and you take a set of orthogonal exponentials, then if D is not congruent to 1 mod 4, then A is finite. If D is congruent to 1 mod 4, the set may be infinite, but it's a subset of a line. So this is an example where a structure theorem for point configuration leads to a structure theorem for orthogonal sets in L2 space of convex bodies.
Sorry, Alex, a quick question just about the wording for that.
Please.
When D is equal, so right, it says if D is equal to 1 mod 4, A may be infinite. So I just want to make sure I understand. Are you saying that the only cases where you could get an infinite A are in that case? Or are you saying that in the case D is equal to 1 mod 4, there is always an A that is infinite?
No, I apologize. This is vague. So this is vague, just trying to save space on the slides. What I'm saying is the former. When D is congruent to 1 mod 4, then there exist examples of convex bodies for which A is infinite. It's certainly not always the case. For example, if the convex body is the ball, then the set is always finite. And we proved that in the same paper.
Right.
Just saying that examples exist. Those examples are sort of man bites dog examples. They have to be constructed just so that it works out. In other words, in any reasonable sense, a randomly chosen convex body with satisfying these properties will not have an infinite A.
Okay, thank you.
Okay. No, thank you for the question. This is a very, very good question. Okay. And okay, and so another point that should be made here is that the application of the Erdős integer distance principle we've just seen gives another proof. In fact, it's an overkill proof that L2 of the ball does not possess an orthogonal basis of exponentials, right? Not only doesn't it have an orthogonal basis of exponentials, it hardly has any orthogonal exponentials at all. Okay, and let me just mention in passing that similar ideas in style were used by Azita Mayeli and myself to prove that there does not exist an orthogonal Gabor basis of L2 over D, where the window function is the indicator function of the ball. Okay, so so if anybody's interested in more about this, please feel free to ask me afterwards. Okay, and these results raise a multitude of questions, the result that I just mentioned. And one of the questions that it raises, which I believe is a question that is very different in nature and requires very different techniques, is just how large can a set of exponentials orthogonal on L2 of the ball possibly be? Okay, and so it is widely believed that the answer is D plus 1. that there's no way to have more than d+1 orthogonal exponentials on the ball. Why d+1? Because, well, Bessel functions do have zeros. So you just construct a simplex where the side length is one of the zeros of the Bessel functions. So you can certainly achieve d+1. The question is, can you have more? I believe that the answer is no, but I certainly have no idea how to prove it. The results in these directions are, even though we worked very hard, are pretty weak. So we know that the number of exponentials is finite, but the proof, even in principle, cannot yield a bound. Okay? And another quantitative result in this direction is a result of Michalis Kohantzakis and myself from 2013, which says that if you do have an orthogonal set and the disk in the plane, and you take this orthogonal set of orthogonal exponentials, intersect it with a square of side length r, then the size of that is less than constant times r to the power of 2/3. So on one hand, this result by itself doesn't even prove that the number of orthogonal exponentials is finite, but it does provide a structural information. It tells us that these exponentials have to be fairly sparse. Okay? All right. So let's keep going. So there was another link between point configurations and the study of orthogonal basis, which was established by Michalis Kohantzakis back in 2004, but the applications only started picking up recently. In fact, there's been lots of them, and I'm only going to be able to mention a few today. A lot of it is work in progress. But here's what Michalis noticed. He noticed that there is a connection, which I'm going to describe, between orthogonal exponential problems and the following configuration problem due to Firstenberg, Katznelson, and Weiss from 1986. They proved the following result. So here E is a set of positive upper Lebesgue density. So it means the usual thing. We intersect this set with the ball of radius r. We divide it by the volume of the ball. We take the limb sup as r goes to infinity, and we insist that this is a positive quantity. In other words, heuristically, it means that your set occupies a positive proportion of Euclidean space. Okay? And what they proved is that there exists a threshold, L, such that for anything beyond that threshold, any L prime beyond that threshold, the distance L prime is realized. In other words, sets of positive upper Lebesgue density realize every sufficiently large distance. So the result was initially proved using ergodic methods, but a very elementary and beautiful proof was later given by Jean Bourgain using Fourier analysis. Okay, and this is Harry Firstenberg. Okay, and okay. So how do we connect? So let me just quickly make a point here. So we've already seen how the Erdős distance problem enters the fray, right? So there, Erdős distance problem tells you that if you have a finite set of discrete points, then it determines lots of distances, right? Here we take so here this is a continuous setting. We take a set of positive upper Lebesgue density, and in this set, we realize every sufficiently large distance, okay? So please keep that in mind, and here's how this enters the picture. So once again, let's go back to the case of the ball, and let's suppose that an orthogonal exponential basis exists. Once again, this means that lambda is separated and has density equal to the volume of the ball. So now just thicken this putative spectrum by a small delta, okay? Then the resulting set has positive upper Lebesgue density. Okay, this is very easy to see. So the Firstenberg, Katznelson, Weiss result implies that every sufficiently large distance is realized. But this is absurd because once again, by orthogonality, we have that the distances between the elements of the putative spectrum are zeros of the Bessel function JD over 2. And these zeros are uniformly separated. Not only are they uniformly separated, they are clustered around half integers shifted by d minus 1 over 8, as I mentioned a few minutes ago. In particular, it is not true that every sufficiently large distance is realized. We have a contradiction, and this gives yet another proof that the L2 of the ball does not have an orthogonal basis of exponentials. So one impression I don't want to give here is that we are sort of a club collecting proofs that L2 of the ball does not have an orthogonal basis of exponentials. It is entertaining, but this is not the point. The point is that each of these proofs sheds a light on the problem and allows us to move in directions that were not previously accessible. So every one of these proofs allowed us to do something we could not do before. Okay? And so let me illustrate something that can be done with this Firstenberg, Katznelson, Weiss approach, and another approach due to Bourgain that I'm going to mention in a few minutes that we could not do before. Okay, so let me. So here's a definition of phi approximate orthogonal basis for L2 of omega. So we say that e to the 2 pi I x dot lambda is a phi approximate orthogonal basis if omega is a bounded for omega bounded domain in Rd, if the set is a basis, and if the Fourier transform at lambda minus lambda prime is not quite 0, but it's bounded by, let's say, phi of the distance from lambda to lambda prime, where phi is a function, is say a continuous function that vanishes at infinity. Okay, so you can think of this. There are more intricate conditions that one can, definitions that one can make, but I want to focus on this one to illustrate the point. Okay, and then one can prove the following theorems. This is joint work with Azita Maeli. So let phi be any function that satisfies limit as t goes to infinity of 1 plus t to the power of d plus 1 over 2. Phi of t is equal to 0. In other words, we insist that phi goes to 0 faster than order d plus 1 over 2. Okay? Then there does not exist a set lambda such that L2 of the ball possesses a phi approximate orthogonal basis. Okay, so in other words, not only does the ball not have an orthogonal basis of exponentials, it doesn't have anything like it. Okay, and again, this is not a talk really on frame theory, but let me mention in passing what some of the motivation behind this is. So one of the big important open problems in frame theory is to prove that not only does L2 of the ball not possess an orthogonal basis of exponentials, which we know, but L2 of the ball doesn't even possess a Riesz basis of exponentials. This problem has been open forever, and it is a significantly harder problem than the problem for orthogonal basis. Just to mention in passing why this problem is hard. So it was proved by Lubarsky and Rashkovsky, I think about 20 years ago, that if you take a disk and inscribe any polygon, so any convex polygon inscribed in the disk with any number of sides, then the L2 of this polygon does possess a Riesz basis of exponentials. Okay, so why should this scare you? This should scare you because roughly speaking, this means that none of the methods you've seen so far have any chance, because these methods are all stable under small perturbations. Whereas the Lubarsky-Rashkovsky result shows that in order to prove that L2 of the disk does not have a Riesz basis of exponentials, we really have to use the fact that the circle is round. And this, at the moment, we do not know how to do. There's some work in that direction that I'm not going to talk about today. This is partly a motivation for expanding these definitions of orthogonality and seeing where they go. So how does one deal with these things? So so you apply Firstenberg, Katznelson, Weiss result to a delta neighborhood of lambda, and you denote it by E delta, and it follows that every sufficiently large distance is realized. But then once again, so this is a sketch, of course, but I think that from this sketch you can really recover the proof if you really wanted to. Using the asymptotic formula for the Fourier transform, we can see that that there exists an R, so that if lambda and lambda prime are in the putative spectrum with the distance bigger than R, then sine of 2 pi norm lambda minus lambda prime minus d minus 1 over 8 is smaller than epsilon. Okay, so what does that mean? So this is just a picture of the thickened set. Okay, so the idea is we have a discrete set, we thicken this set, and this gives us the set of positive upper Lebesgue density, and then we deduce consequences from this. So this is one of my favorite things to do. Take a discrete problem, turn it into the analysis problem, use the ugly machinery of analysis, and then go back. Okay, why do I call analysis machinery ugly? Because I mean, I guess I hang out with lots of algebraists and discrete mathematicians, and they call it ugly. Okay, and so it follows that for some positive integer k, the distance from lambda to lambda prime is k over 2 plus d minus 1 over 8 plus big O of epsilon. And from that, we can deduce that the distance from x to x prime in the continuous version of the set, the distance is again an integer over 2 plus the dimension minus 1 over 8 plus big O of epsilon plus big O of delta. And if epsilon and delta are taken to be sufficiently small, then any sufficiently large distance L cannot be realized in this set. And this once again leads to a contradiction and establishes the theorem. And so according to my calculations, I have 6 or 7 minutes remaining. Is this correct?
You have about 8 minutes left.
I have about 8 minutes, okay. Because as I've told you before the talk started, my advisor, Chris Salk, taught me that finishing on time is an absolute must. And so this was kind of, he drilled into me. So I'm going to endeavor to absolutely finish on time, and I think I'll be able to. Okay, and so I would like to mention just one more connection with point configurations, which involves a really beautiful observation by Jean Bourgain. And so as I say here, as we dig deeper, more and more configuration scenarios come up. In other words, another point I want to make is this is not a case where at some point we notice that configurations are useful in these problems, so we just keep looking for scenarios where they come up. These things come up naturally. It's not my fault. Okay, and so the previous result that we discussed involved approximate orthogonality in the sense that orthogonality held up to a small pointwise error. So one question one might ask, if you want to loosen these constraints, is what happens if approximate orthogonality only holds on average? Okay, and I'm going to state the precise condition in a moment. But as it turns out, that once you replace a pointwise condition on almost orthogonality with an average condition, then Firstenberg, Katznelson, Weiss is no longer the right tool. And the right tool is a refined version of Firstenberg, Katznelson, Weiss, which was established by Bourgain. So I'm going to state it later, but what I stated a few minutes ago is the result by Firstenberg, Katznelson, and Weiss that any set of positive upper Lebesgue density determines every sufficiently large distance. What Bourgain proved is that under the same assumptions, you can actually, there exists a point in the set. In fact, for most points in that set, in the Lebesgue sense, you can pin this point and all the sufficiently large distances to this point are realized. Okay, now Bourgain only proved this in the 2-dimensional case, and he only proved this for Euclidean distances, but this has frequently happened with Bourgain. He established a principle and he respected the fact that other people need to make a living also. So, so his result readily generalizes to higher dimensions and to more complicated metrics. Okay. All right, so here's the theorem. And so this theorem is rather technical, but the point I want to capture here is that it requires the use of this more sophisticated point set technology. So A is a separated subset of Rd, and P is any exponent between 1 and infinity. K is a bounded symmetric convex set with a smooth boundary and everywhere non-vanishing Gaussian curvature. Phi is a continuous monotonically non-increasing function such that for some sequence going to infinity, you have this average condition. So the LP norm of phi on this interval, Rj to 2Rj, normalized, is bounded by some epsilon times Rj to the minus d plus 1 over 2. And if j is sufficiently large. And so what is phi? Phi is that which dominates the Fourier transform of A minus A prime, where A is this given separated subset of Rd, okay? And once again, rho star is the Minkowski functional on the dual convex body. Then the upper density of capital A is equal to 0. And in particular, e to the 2 pi I x dot A is not a frame for L2 of K. So once again, this theorem is in the genre that not only does L2 of K under these assumptions not have an orthogonal basis of exponentials, it doesn't have an even approximately orthogonal basis, even in a very weak sense, okay? And so this result follows from a technical variant where again, K is as before, Brj and B prime Rj are balls of radius Rj separated by 3 Rj. And then there exists a constant C such that the summation, so now the average is not of integrals, but of sums on the spectral side, is bounded by constant Rj to the minus d plus 1 over 2. Then we can conclude that the upper density of A is equal to 0, okay? And to conclude the talk, let me just briefly describe how Bourgain's result comes in on pinned configurations. So as before, by the method of stationary phase, we have the decay of the Fourier transform of order minus d plus 1 over 2. And it follows from that the assumption of the theorem, if you trace this assumption, it holds for some constant. The point is that if it holds for small enough constant, we have a problem. It will definitely hold for a larger constant, but it's a small constant that creates difficulties because it's a small constant that forces the sign in the asymptotic of the Fourier transform to be small, okay? And so if that happens, then we can invoke the asymptotic formula and argue that sine of 2 pi of rho star A minus A prime plus D minus 1 over 8 is small quite often. And the difference between quite often and always is that we now have to use pigeonholing methods, and we have to use them very carefully, okay? And by using pigeonholing, what we can conclude is that there exists a point living in a small neighborhood of the point of the putative spectrum, so that pinned distances from this to the small neighborhood of a positive proportion of A is clustered around half integers plus d minus 1 over 8. And here we derive a contradiction by using a pinned variant of the Firstenberg, Katznelson, Weiss that was proved by Bourgain. As I said, Bourgain proved it in 2 dimensions for the Euclidean distance, but if one is familiar with the technology of maximal operators and harmonic analysis, it does not take a tremendous amount of effort to extend it to higher dimensions. So just as a final technical comment, roughly speaking, the difference in terms of the proof of the Firstenberg, Katznelson, Weiss and the pinned version of Firstenberg, Katznelson, Weiss proved by Bourgain is that Firstenberg, Katznelson, Weiss, if you look at it the right way, reduces to Sobolev mapping properties of the spherical averaging operator. However, if you want a pinned version of Firstenberg, Katznelson, Weiss, you have to use Sobolev mapping properties of the maximal spherical averaging operator. And that is a much more sophisticated problem, especially ironically in 2 dimensions. It's easier in higher dimensions. Okay, so I was hopefully able to give you at least a small sliver of the connections between point configuration problems and problems in frame theory. And I think I'm going to stop there.
Thank you for the great talk, Alex. Just a reminder to everyone, so we're going to have time for questions now, but you are all welcomed and encouraged to stay on afterwards for a bit of socialization time. It's good to catch up with people. But so now we'll open the floor. Any questions for the speaker?
Yeah, so I have a question. So actually I have many questions because of the last comment of you. So there's some socialization, social distance, some social event afterwards. How long is it?
Oh, because it's for about a half past the hour. So we do about a half hour after questions.
Unfortunately, I would say, unfortunately, I'm sorry.
Yeah, no, I didn't mean to interrupt. All I wanted to tell you is that don't worry about the time. I'm very easy to find. Send me an email. We'll jump on Zoom, and we can talk as much as you want. I'm always happy to discuss these things.
That would be great because my third question would be much longer. So I probably send you just an email and just ask a question here that's interesting for the audience. Sure. Yeah, unfortunately, I have to go to a Corona test in 10 minutes, so I cannot go with you to the social event. Okay, but let me ask the mathematical question. The first was, you said you are not a group of people collecting proofs for the ball. So let me ask, is there another type of body that is in the same way important? So I understand that the ball is a very natural question, right? But is there another type of sets that has the same popularity, so to say?
Well, the thing is that, okay, so let me, here's one way of answering your question. Let's talk about convex sets. In the realm of convex sets, it is now known that the only convex sets for which orthogonal basis of exponential exists are the ones that tile RD by translation. And due to a theorem of Venkov-McMullen, again, it depends on whether you're from the East or West, you know. So okay. By a theorem of Venkov-McMullen, it is known that it is known exactly which convex polytopes tile RD, and they have to be polytopes. That's very easy to prove. So in other words, the similar results can be proven for basically anything that is not a convex polytope. However, there are nuances, because for the bowl, we have much more intricate information, right? So once you start talking about the number of orthogonal exponentials, right? Then of course, so for the bowl, the conjecture is d+1. If you take a convex body, which is much flatter than a bowl, but is not quite a polytope, then this property could change. So you see what I'm saying? In other words, many of these results hold in much greater generality, but A, they're much harder to prove, and B, they're even harder to state. They're even difficult to state.
Thank you. And let me pose my second question.
Sure.
Because it's about the orthonormal sets in the trigonometric system, so to say, but without any normalization or something, and you always consider the Lebesgue measure, right? And
sure.
Is it of the same type of interest if you say change the measure, or just say if you want to have a basis of exponentials, but in L2 with the measure or something?
Okay, so there are two quick comments here. First of all, for general measures, there's some really interesting work on this, and that's a long story. We can discuss this separately. Also, a lot of it is work in progress that I'm doing right now. And a lot of it is related to the uniformity of distribution, etc. In other words, subjects that are relevant would be relevant for this seminar. I just didn't quite finish that paper. That's the paper I really wanted to talk about. And so there are results that connect what you're talking about to discrepancy theory. Okay, but this is something that I will hopefully be able to discuss in the future. But another point is that if you're in the realm of sets of positive Lebesgue measure, then one might wonder if anything changes if you introduce a weight, let's say wx dx, instead of just a measure dx. And this is, again, one of many instances when there is a simple but absolutely beautiful argument by Michalis Kolantzakis, which shows that there's no difference whatsoever.
Thanks. Let me just give a comment why I'm asking that, because together with David Krieg, I will give a talk in the series later, I'm not quite sure, in some months or so, about this project. We had some trouble. We were talking about approximation theory using function values. So one of the third side of the coin you were talking about today, so to say. And we had quite some trouble to tackle unbounded basis functions, which are just exist for depending on the space you have, right? Depending on the space of functions you have. And we did exactly something like that. We introduced a weight, so everything is bounded at the end. And so, yeah. Not quite connected.
I see that we have a lot to talk about.
I'll send you an email right now.
Okay.
Bye.
Thank you very much.
Other questions?
Yeah, I have one question to Alex. So in the theorem, there is a threshold so that after that threshold, each distance is attained if the upper density is positive. So what does this threshold depend on? I mean, does it depend on the density or? Yeah,
it depends on density. If you go through the proof, it is so the threshold that the proof gives is almost certainly not sharp. In fact, it's not sharp, but it has to depend on density. So just take integer lattice and thicken it by delta, right? So it's clear that you are not going to get distances that are smaller than square root of 2, for example. But also you can pretty quickly see that you're not going to get even some larger distances. So it pretty clearly depends on density. But exactly how it depends on density is a tricky business. In other words, among all the sets of a given density, which is the worst set with respect to this property? I think that's a separate and highly non-trivial question. Basically, anytime you start asking concrete optimization questions, and this is something people in this seminar know very well, these questions can be arbitrarily difficult.
Okay, thank you.
No
problem at all. Other questions?
So yeah, I have a quick question about this weird phenomenon about D equal to 1 mod 4. So this is because of the shift in the Bessel function, right? Because of the phase shift, D minus 1 rate, right?
Yeah.
So,
yeah, this is one of my favorite things. Yeah.
So where else does it arise, and is there some deeper explanation of this other than taking the Bessel function and looking at it? Is there some philosophical explanation why D equal to 1 mod 4 is a special case?
This is a great question. And the first time we had this discussion was roughly in 2005. And ever since then, I've been seeking an answer to this question, right? So there's this, there's this great story about Diogenes in ancient Greece walking around with a lantern in daylight looking for an honest person. In the same way, I've been looking for an answer to this without much success. In other words, where does D minus 1 over 8 arise from? It arises from the signature of the quadratic form after the application of Morse's lemma in the proof of the method of stationary phase. In other words, there's no mystery where it comes from. The real question is what does that mean? And like you, I'm never satisfied with statements like it doesn't mean anything, it's just this. There must be a meaning, and I will keep searching for it. Whether I find it before I die is a different question.
So I saw at least a few other papers where this same effect arises. So I think there is some paper by Skriganov and co-authors. There is a paper by Travaglini and William Chen about discrepancy with respect to disks or balls where a similar effect arises. Yeah, and it's clear that it arises from this computation with the Bessel functions or the signature if you're doing more general convex bodies. Yeah, but still, I'm not satisfied with this somehow.
No, there's something deeper here. Basically, there's a hint that these are just sort of shadows of a much deeper, more general phenomena. But one thing that I find heartening is that occasionally one finds these things. Like in graduate school, I wondered why the sharp exponent for the spherical maximal theorem is d over d minus 1. So why does it converge to 1 when d goes to infinity? What does that mean? And I eventually discovered that there's this phenomenon in probability called concentration of measure. So that in higher dimensions, more and more of mass of the ball is concentrated near the boundary. And then came the proof of Wilhelm Schlag, geometric proof of the maximal theorem, where all of this comes together. So occasionally these questions get answered. Just this one is still open.
Yeah, thanks.
I have a question. This is related to the Firstenberg, Katz-Nelson, and Weiss theorem. Did I get the names right? So the requirement in that theorem is that your set having positive upper Lebesgue density, right?
Yeah.
But it works in any dimensional Euclidean space, right?
Yes.
So do you know if there are any results that somehow allow you to replace upper Lebesgue density in RD with some kind of lower dimensional Hausdorff density, I guess?
No. So yeah, it's an excellent question. So the answer is yes, but it's tricky. So there is, of course, the Falconer distance problem, right? Which says that if the dimension, Hausdorff dimension is big enough, then the Lebesgue measure of the distances is positive. Right. So roughly speaking, the chain of reasoning goes like this. The theorem, the Firstenberg-Katz-Nelson-Weiss theorem, is stated in the large, right? But it's really a local theorem. It's really a local theorem. The only reason it looks global is because the Euclidean distance is homogeneous. So you can with a little bit of work, and I can tell you about it or send you references, you can easily translate it into a compact statement about a subset of the unit square of certain measure, right? And in that context, you can sort of see in front of your eyes, so to speak, the transition from that statement to Falconer. In other words, what you're really talking about is how does Firstenberg-Katz-Nelson-Weiss, how does it transform into Falconer distance problem? And the exact details of this are far from clear, but this is what we are talking about.
Okay. Yeah, okay, that makes sense. Thanks.
Sure.
Any other questions for the speaker?
I have a small question. It was from the result from 2020. And here was the limit of function phi and multiply 1. Yeah. Why do you have here like d plus 1 over 2? And is it important that just this limit like tends to 0, or it tends to 0 as some like logarithmic function or like power function?
No, that's an excellent question. This is one point that I wanted to make more clear, and I didn't do so. So I'm really glad you asked. Here's the point. The decay, so if we go back here, the decay of the Fourier transform is minus d plus 1 over 2. Okay? So in other words, so that decay is always there. So the Fourier transform is always bounded by this. But the Fourier transform is not just the decay, it's decay times times the sine function.
Mm-hmm.
So what we are saying is, is that if the Fourier transform decays any faster than d+1/2 on the difference of the elements of the spectrum, then you get a contradiction. So the Fourier transform is this decay times the sine function which oscillates. Okay, and so the meaning of the d+1/2 is that if your Fourier transform evaluated on the different set of the spectrum is any smaller than what is given by the pointwise decay, then it's a no-go, and that set cannot give you a frame.
Okay, thank you.
So that's the meaning of d+1/2. And no, you don't need any extra logs there. The moment you drop below d+1/2, it's game over using Firstenberg and Nelson-Weiss.
Okay. And I have another question. Do you
Sure.
know some other examples when Fugler conjunctions holds?
Oh, okay. So when it holds, it holds for, so in dimension 1, it holds for unions of intervals. I don't remember if it was proven for arbitrary union of intervals, but it was proven for unions of intervals under many assumptions, which means that in dimension 2, it holds for unions of rectangles under a variety of assumptions. I don't think the problem has ever been completely solved there, but and also for convex sets. I am not aware of any other easy to state. So what you might be thinking is, given how few examples there are of when it holds, why did all of us believe for 25 years that it held? I don't know. So I mean, we were not clever enough.
Alex, is it disproved in all dimensions?
It's this. Oh no. So this is a very good question. That's also a very good point. It is disproved in dimensions down to 3. In dimension 2, it's not disproved.
Yeah, that's what I thought.
And in dimension 1, it is not disproved. Also, there's another little tantalizing tidbit, is that the way it was disproved is it was disproved in Z mod P, in vector spaces over Z mod P. And it was disproved in Z mod 5, then it was disproved in Z mod 4, then in one directions in ZP3, but then Azita Mayeli and I proved that it's true in ZP2. Now, does that shed any light on whether it's true in R2? I would say no, that would be a reach. I mean, I didn't even try to sell this idea to the NSF. I mean, this is, this is a stretch. I mean, ZP2 is really just not a good model for R2. And, but nevertheless, it is intriguing. In dimensions 2 and 1, there's still, if I had to guess, I would say that it's probably false in 2 dimensions, but until it's proven, yeah, it's a good point.
Thank you. Yeah.
All right, any other questions? All right, well then I'm going to stop the recording in case